Hi, today I want to talk a little bit more about capacitors. In particular, we're going to study the simplest kind of capacitor, the parallel plate capacitor. And why do I want to do this? Well, we've already seen that capacitors are capable of storing charge. If you hook them up to a battery, they store charge. And, to put charges all together in the same place, that requires energy, so they must also be able to store energy. So they're useful devices for storing energy, and they have a wide range of applications in all sorts of technologies. For example, pacemakers use capacitors. A defibrillator is basically a capacitor. There's capacitors in our phones and our computers, all sorts of things. So these are very common devices. Let's say I have a battery. So here's my battery. And I have wires coming from my battery, and I'm connecting them to a couple of really big plates. So here are the plates of my capacitor. Okay. Let's say that they are a certain distance d apart, and each plate has has an area A. Okay? And let's say that this battery maintains a fixed potential difference, call it V. Okay, now this is the positive terminal of my battery, negative terminal of my battery, so this top plate is going to acquire a positive charge, some amount Q, and which means due to charge conservation, the bottom plate must have an equal but opposite charge. It should make intuitive sense that if I have a stronger battery, if I increase V, then I'm going to increase Q, right? The more potential difference, the larger amount of charge on each of the plates. And so it shouldn't be terribly surprising that the charge on the plates is directly proportional to the potential difference that the battery maintains. And there's some constant of proportionality here that I'll call C. Turns out this constant of proportionality has a name. It's called capacitance. Not surprisingly, capacitance is equal to Q over V. So it's basically a measure of how much charge my capacitor can store per volt that I have in my battery. Right away, you can tell what the units of this new quantity is going to be. It would be coulombs per volt. That has a name. We call that a farad, which we can shorthand F. Okay? So this is our definition for capacitance. A larger capacitance for the same voltage will have more charge. Not terribly surprising. Now, what else is going on here? Well, we know that between the plates we're setting up an electric field, right? And we already found out, in fact, so here's my electric field, we already calculated what the magnitude of that electric field would be. It's equal to sigma over epsilon 0. We got that from Gauss's law. But sigma, remember, is just charge per unit area. Right? So if I know the area of my plates, I can write this as Q over A times epsilon 0. Right now I'm just playing around with the things that I know about capacitors, right? So it's free, we can do that. But this is a useful relation, so I'll put a circle around it. This is obviously a useful relation, so I'll put a circle around it here. So these are all formulas that relate to the various quantities of our capacitor. Another one that's useful is that E is equal to delta V over delta S. Remember this? That there's a very straightforward relationship between the electric field and the change in the potential over some change or over some displacement. This means that delta V is going to be equal to negative E times delta S. And so let's imagine this is point A, this is point B. If I go from top to bottom, right, then delta V would be V bottom minus V top, which in this case would just be negative V from the battery. That would be equal to negative E times delta S, which in this case is D. So really this comes out to a very simple expression, V equals E times D. So I'll put a circle around that too. So right now, already, just by playing around a little bit, I have three useful relationships between the various quantities in my capacitor. Now, I can actually, if I go back to this expression over here, I can actually get some more useful stuff. In particular, if I solve this equation for Q, plug it in there, and I plug this in for V, then I can actually get C in terms of these other things. And so let's try that. And so I can solve that first equation that I had circled over here for Q, E times epsilon 0 times A. That's just solving for that. And then I had V equals ED. So actually, if I plug this stuff in over here, I've got C equals E epsilon 0A divided by E times D. The E's cancel, and I've also got E in terms of the physical dimensions of the capacitor. So all these things I'm circling here will be potentially useful when we're talking about parallel plate capacitors. They're all related. But what you can see is that the capacitance really only depends on the physical properties of the device that I'm building, right? It depends on the area, it depends on the distance between the plates, and it depends on a fundamental physical constant. If I take just some typical values and I plug them into this formula, for example, if I imagine that the area of my plates is about 5 square centimeters, and the distance between my plates is about 2 millimeters, if you plug that in, you'll find that the capacitance winds up being about 2.21 times 10 to the minus 12 farads. Pause for a second and see if you agree with my number, because there actually is a lot of students have an issue when they actually come to convert the area here, so be careful about that. Make sure you can figure out why it's this and not some other exponent. But anyway, you can see that this is actually a very small capacitance. 10 to the minus 12 is the metric prefix pico, so this would be 2.21 picofarads. So for these rather reasonable values, 5 square centimeters and a couple of millimeters separation between the plates, right? This is certainly something that you could fit in your pocket. You get a very small number for the capacitance. It turns out that the unit for capacitance, the farad, is actually a very large number. 1 farad is a huge capacitance, right? You don't typically see things that have a 1 farad capacitance. When you're talking about that, you're typically dealing with microfarad, or maybe at the most millifarad. In fact, if you were to try to build, say, like a 1 farad capacitor with just like a 2 millimeter separation distance between the plates, you would need huge plates, right? I haven't done the calculation, but you could do it. It's probably something about the size of the state of Illinois. I mean, a huge plate, not particularly convenient for sticking in your pocket and having in your iPhone and things like that. So there must be some other way to beef up the capacitance of a device like this. And in fact, there are several ways that you can do it. One way to do it is to alter the geometry a little bit. For example, you can take these 2 plates and bring them really close together and then roll it up like a giant sausage. And by doing so, increase the area of the plates rather considerably. But in fact, there's another way to do it too, and that's to put between the plates a device called a dielectric. So what is a dielectric? Well, a dielectric is actually just any insulating material. It's just a way of saying an insulator, meaning that the atoms in a dielectric or an insulator, the electrons in those atoms are strongly attached to the nuclei, and so they're not free to roam about as they are in metals. And we've already seen actually what happens when you put an insulating material in an electric field. In fact, if we zoom all the way down to an individual atom inside of an insulator, if you apply an electric field, let's say that's down, in the absence of an electric field, the electron would be spherically symmetric around the nuclei. It would not want to spend any more time on top or on bottom or left or right. It would just sort of uniformly distribute itself. But in the case of an electric field, if we put that atom in an electric field, then it tends to get stretched where the nucleus is down here and the electron tends to spend more time up here than down here, because the electron is going to get pulled towards in the opposite direction of the electric field and leaving the nucleus down here. So you get this sort of separation, you get this polarization of the individual atoms inside of a dielectric. So if you look at this on a grander scale, here's my slab of insulating material. Here are all the individual atoms, the positive charges, the positive nuclei, and basically the electrons are going to be sitting right on top of them. And so this is in the absence of an electric field. But if I apply that downward electric field now, if there's now a downward electric field, then a nuclei, then the electrons, there's going to be a separation between the positives and the negatives if we have a downward electric field. Now if I sort of circle this region right here, in this green box that I just drew, if you count the total number of pluses and minuses, you'll find that it's neutral, right? What you have then on the top is a very, very tiny little positively charged or negatively charged layer, and on the bottom you have a positively charged layer, right? These are in fact called the induced charge layers. Okay, so it may not seem like much, but let's see what then happens if I were to place such a material between the plates of my parallel plate capacitor. Okay, so first of all, no dielectric. Here's the top plate and the bottom plate, plus Q, minus Q. And I've set up an electric field, right? Let's call the magnitude of that electric field E0. And let's call the potential difference between these two plates, let's call it V0. Right? And now let's put this slab of insulating material inside the plates of my capacitor. Okay, so now I've got the and let's say that in this process, I keep the amount of charge on the plates fixed. So it's still plus Q and plus Q, minus Q, minus Q. This must mean that I've actually disconnected it from anything else, right? So the charge is stuck on those plates. And now I put the dielectric inside. So here's my slab of insulating material. And let's imagine that it completely fills the space between the plates, right? Well, what's going to happen? Well, we're going to have the exact scenario that I just drew in the picture before. We're going to have insulating material in the presence of a downward electric field. So what's going to happen is I'm going to get that negative induced charge layer up here and the positive induced charge layer down here. But you can see that what that's going to do, that's going to create sort of a secondary electric field, right? So here's my original electric field. In red here is my E0. That's the original field. But in addition to that, I'm going to get a secondary electric field inside the piece of plastic that goes from the positive induced charge layer to the negative induced charge layer in the opposite direction. Right? You can probably imagine what would happen then if I added that secondary field to the original field. I got something that's down and something that's up. Now you might initially think that the two fields would cancel, and in fact they would cancel if this were a piece of metal. But because it's an insulator, the size of these charge layers will vary depending on the substance. So you may not be able to completely cancel out that original electric field, but you ought to be able to make it much weaker. In fact, the electric fields in the dielectric is definitely going to be less than E0. Right? The free field without the dielectric, right? And in fact, the electric field inside the dielectric will be less by a certain factor that I'm going to call kappa, right? Kappa is called the dielectric constant of the material. It's a dimensionless quantity. It has no units, and it's just a measure. It's just a property of the material. Right? It's just a measure of how strongly the dielectric responds to the presence of an electric field. One thing that is always true, though, is K is going to be greater, or kappa is going to be greater than 1. Right? We definitely want E inside the dielectric to be less than E0. So in order for that to happen, kappa always has to be greater than 1. And kappa is something you can just look up in a table, right? I mean, it's got depending on the material that you have, it'll be something else. For air, for example, if this is just air, if it's not a vacuum, but if it's air, the dielectric constant is 1.00059, so very close to 1, which is why we can treat more or less an air-filled capacitor the same as a vacuum-filled capacitor. We don't really bother distinguishing between vacuum and air in the world of capacitors. But when you get something like glass, the dielectric constant for glass is something like 5, so that's going to represent a drastic reduction in the electric field magnitude inside the dielectric. For water, it's something like 80, right? That is actually related to the fact that water has its unique own dipole moment, but of course you're not going to want to stick water between the plates of anything electric because it turns out it has a very low breakdown voltage, and so it's dangerous to use. So, if the electric field between the plates goes down, then since V equals E times D, if E goes down, then V goes down. So that means that V is going to be less than V0, right? That is, the potential difference between the plates in this scenario is going to be less than the original potential difference between the plates. In fact, it's going to go down also by a factor of kappa, because I haven't changed D. And since the capacitance is equal to Q over V, if Q remains fixed but V decreases, then you can imagine that C, this capacitance of my new device, is going to be greater than the original capacitance. In fact, C is going to go up by a factor of kappa. So my new C with the dielectric present is going to be kappa times C0, which is the capacitance without the dielectric present, right? So these are all, so you can see that we've actually done it by putting in that piece of plastic. We've effectively beefed up our capacitor by a factor of kappa. We've made it a stronger capacitor. It can store more charge for the same voltage. So that turns out it's a very useful thing, these dielectrics. Okay.